Wind power has great potential. It provides clean energy to homes around the world and is one of the most important energy sources in the fight against climate change. But do you know how it's produced? What exactly are wind turbines and how do they work? Let's find out. First up, what is a wind turbine? Wind energy has been harnessed for millennia to generate mechanical power. Egyptians harnessed wind energy to drive boats along the Nile River as early as 5000 BC, while windmills were used by American colonists to grind grain, pump water, and cut wood at sawmills. Wind turbines are the modern equivalent of windmills, transforming wind kinetic energy into clean, sustainable electricity. How does a wind turbine work? The majority of wind turbines are made up of 3 blades attached to a tubular steel tower. There are several variants with 2 blades or with concrete or steel lattice towers. The tower, which is 100 feet or more above ground, permits the turbine to benefit from stronger wind speeds seen at higher altitudes. Turbines capture wind energy using propeller-like blades that function similarly to an airplane wing. A pocket of low-pressure air arises on one side of the blade when the wind blows. The blade is then drawn toward the low-pressure air pocket, forcing the rotor to turn. This is referred to as lift. The force of lift is substantially greater than the force of the wind against the front side of the blade, which is known as drag. The rotor spins like a propeller due to the combination of lift and drag. A set of gears increases the spin of the rotor from around 18 revolutions per minute to 1800 revolutions per minute, allowing the turbine's generator to create alternating current, AC. A nacelle is a streamlined shell that houses major turbine components, which typically include the gears, rotor, and generator. Some of the nacelles atop the turbine tower are large enough for a helicopter to land on. Another important component is the turbine's controller, which prevents motor speeds from surpassing 55 miles per hour in order to avoid damage from high winds. An anemometer continuously detects wind speed and sends that information to the controller. In an emergency, a brake, likewise placed in the nacelle, physically, electronically, or hydraulically stops the rotor. Now for horizontal axis wind turbines. HAWT, HOT. The most common type of wind turbine is a horizontal axis wind turbine. A shaft, generator, and blades are among its components. The blades are designed to face the wind. The wind strikes the blades, forcing the shaft to rotate. A gear attached to the shaft turns on the generator, and electricity production begins and is supplied to the power grid. Some major elements of the wind turbine contribute to its efficiency. The nacelle, also known as the head, has a wind vane, an anemometer, and a controller that measures the wind speed and direction. When the winding route changes, a motor spins the nacelle to ensure the blades face the wind. In high winds, a brake on the turbine slows the speed of the shaft. In extreme situations, the brake protects the turbines from harm. Horizontal axis turbines have 3-blade airplane propellers. The largest is approximately a 20-story structure with 100-foot-long blades. The more electricity produced, the taller the turbine. The horizontal form is nearly universally utilized in turbines. Next, we have vertical axis wind turbines, VAWT, VOT. The shaft and blade of a vertical axis turbine are vertically attached to the ground, along with all of the essential components. Even the wind turbines themselves are close to the ground, which is quite unlike horizontal axis wind turbines. Vertical axis wind turbines are classified into 2 types: lift-based turbines and drag-based turbines. The drag or paddle-based designs are less efficient than the lift type. Vertical axis turbines are shaped like an egg beater with blades attached to the top and bottom of a vertically arranged rotor. These turbines have fewer parts than ones with horizontal-oriented rotating mechanisms and blades. That implies there are fewer parts to wear out and break. Also, because the gearbox and generator are close to the ground, the tower's supporting strength is reduced. Pitch and yaw control parts are also not required. The turbine does not have to face the correct wind direction either. Air flowing from any direction or speed can rotate the blades in a vertical arrangement. As a result, the system can be used to generate power in both gusty and steady winds. Now on to wind turbine applications. Wind turbines are used for a variety of purposes, such as capturing offshore wind resources to generating electricity for a single home. Even large wind turbines, which are typically utilized by utilities to supply power to a grid, range in size from 100 kilowatts to several megawatts. Utility-scale turbines are frequently clustered together in wind farms to generate substantial amounts of electricity. Wind farms can have a handful or hundreds of turbines, with enough electricity to power tens of thousands of houses. Small wind turbines of up to 100 kilowatts are often located located near where the electricity generated will be consumed, such as near houses, telecommunications dishes, or water pumping facilities. Small turbines are occasionally linked to diesel generators, batteries, and solar systems. These systems are known as hybrid wind systems, and they're often employed in distant, off-grid places where a utility grid connection is not accessible. Many countries deploy offshore wind turbines to harvest energy of strong, constant winds found off coastlines. For example, the technological resource potential of wind above U.S. coastal waters is sufficient to generate more than 4,000 gigawatts of energy, or roughly 4 times the existing generating capacity of the U.S. electric power system. Despite the fact that not all these resources are being utilized, this represents a significant possibility to deliver power to densely populated coastal communities. Finally, we have some other innovations in wind turbines. Diffuser augmented wind turbine. A diffuser augmented wind turbine is outfitted with cone-shaped wind diffusers to improve the efficiency with which wind power is converted into energy. The diffuser enhances the speed and hence the efficiency. Rotor blades in conventional bare turbines are positioned vertically on the support shaft or tower. In the diffuser augmented wind turbine, however, rotor blades are installed in the diffuser. It is then installed on top of a shaft or support tower. More changes to the diffuser have been made to boost the device's efficiency. Twin-bladed rotor. A 3-bladed rotor is used by nearly all current wind turbines, but there are few with 2 blades. Groy 1 was a 2-bladed unit tested at Kaiser Wilhelm Kug in Germany from 1983 to 1987. Emerdic Wind Park near Zeewold, Netherlands, used the 2-bladed turbines. Nordic Wind Power, which created models such as the N100, was a manufacturer of the 2-blade turbines. Other turbines have also been produced by Nedwind. Downwind rotor. When the wind blows, almost all wind turbines have a rotor situated in the nacelle front. The rotor in certain turbines is located behind the nacelle. The design is advantageous since the turbine aligns with the wind, lowering costs. The drawback is that the strain on the blade changes as it passes behind the tower, including the fatigue load and resonance in the turbine's other parts. Coaxial multimotor. More than 3 rotors can be installed in the drive shaft. As the wind flows through each rotor, they are combined by the space between an angle from the wind's direction. Douglas Selsom's 2004 research demonstrated the coaxial multirotor produced a significant quantity of power. The first one was utilized in California, with the propellers separated by 12 feet. The diameter was 2.1 meters due to the new rotor. Iowa State University aerospace engineers, among others, have optimized the turbines. The turbine increased power by 10 to 20%, but was less efficient than the counter-rotating design. Counter-rotating horizontal axis. When a mass is propelled in one direction, propulsion is produced in the opposing direction. There is a substantial amount of rotating air present. Too much tangential airflow is wasted in a single rotor. An extra rotor is added to increase the production of an extra power, making it more useful. Another benefit of contra-rotation is the elimination of a gearbox and auto-centering on the turbines. The turbines in the counter-rotating horizontal axis are arranged on the same side, with the front inclined to avoid colliding with the other ones. When the blade is on the other side of the tower, the back blades should be smaller than the front blades. To avoid vibration, the turbines should turn at a 7:3 ratio, with few common multiples. It enables the generator to operate across a wide speed range. Savonius wind turbine. Aerofoils are positioned vertically on the shaft and grounded on a station in the turbine. The turbine has an S shape from above and turns slowly. It can grind grains, pump water, and perform other duties. Because of the wind turbine's slow spin, no power is produced. Flapping panel wind turbines. A flap turbine, also known as a check valve turbine, is a vertical axis turbine with movable flap blades. When the blades are joined together, they form a sail. When the wind blows, the flaps close, preventing wind from passing through the sail. Because the wind is blocked, the turbine begins to rotate. Gyro mill turbine. 2 or 3 airfoils mounted vertically to the center with horizontal support power a gyro mill wind turbine. It works well in windy circumstances and is cost-effective solution. The normal horizontal axis windmill is inadequate for this type of turbine. And that's a wrap for this video. What do you think? Is wind power the renewable energy to replace fossil fuels, or do you have faith in another source beating out wind? Do let us know in the comments below. Make sure to give this video a thumbs up and click the subscribe button for more videos like this. See you in the next one.